Hello everyone, and thanks for the introduction. What I'm going to be presenting in this work is really a continuation of what Andrew discussed in his earlier work about Ensemble Kalman Inversion, which is to apply certain regularization techniques to aid the actual inversion in EKI. Now, regularization is a very important tool, and it's used in a lot of different applied mathematical disciplines. And some of the reasons why it's helpful is because it helps alleviate stability issues, but as well as this, it can also incorporate certain prior information of your unknown as well. And in particular, for this presentation, I'm going to apply one form of regularization, which is Tikhonov. Now, Tikhonov is one of the most well applied as well, but also in the case of inverse problems, it is one of the most well understood as well. And it's exactly for these reasons why we base the motivation of understanding Tikhonov regularization within Ensemble Kalman Inversion. And what I really want to aim to show you from this presentation is how we can systematically incorporate this form of regularization to EKI and what sort of insights we can get. And what I mean by this is in terms of analytical insights, but also to show numerically if we can verify that this improves the level of inversion as well. Now, before I begin the presentation, I just want to say that this is joint work with Andrew, but also Shin Tong, who is at NUS in Singapore. Now, the real motivation behind this presentation goes to the ideas of Ensemble Kalman Inversion and inverse problems. And as these have already been discussed quite readily in the presentation, or the conference, should I say, I'm just going to discuss them in a very brief manner in the next few slides. So, as it's already been stated, inverse problems can simply be thought of as a parameter estimation problem. And the inverse problem, which is given on the board right here, is interested in the recovery or reconstruction of some unknown quantity u from noisy measurements given by y. And y is given in this exact first equation right here, where y equals g of u plus eta. Eta is represented through additive Gaussian noise. For the case of inverse problems, you don't have to assume that it's additive or Gaussian, but for the purposes of my work and this presentation, we are going to assume these two things. And g is just an operator between the parameter space to the observational space. Now, an obvious question to ask from this is, how can you actually approximate solutions to inverse problems? Well, usually there are two main approaches that you can do to answer this question. The first is the classical approach, which if you take your inverse problem, you characterize a least squares functional from this, and then the solution of your inverse problem is essentially the minimizer of this functional. And this is known as the classical or deterministic approach. And the other approach which you can think of is the Bayesian approach, which instead of characterizing the solution as a minimizer of a functional, instead you characterize it as a probabilistic distribution of the random variable u given y. And this is given just in the bottom equation right here, where it's in the form of a posterior distribution, which you can write in this form through Bayes' formula. And just on the right-hand side, you have the likelihood, which is the probability of y conditioned on u, but also you have the prior, which is the probability of u. And I've just written on the board right here a number of advantages or disadvantages that you can think of with these two different approaches right here. So some common optimization approaches which are used for determining inverse problems include whatever your favorite gradient method is, or whatever your favorite derivative-free method is. Examples include the Quasi-Newton method, Land-Weber methods, and also, let's say, conjugate gradient methods as well. And common Bayesian methods which are used to solve inverse problems include Markov chain Monte Carlo, but also sequential Monte Carlo as well. Now, what my research has really entailed has been looking at an inverse problem, or an inverse solver, which really lies in the middle between these two. It's really an optimizer, but you can incorporate certain uncertainty quantification techniques within it. So from that, I sort of view this as sort of a mix between the optimization procedure, but also the sampling procedure. And this, as described in the morning, is Ensemble Kalman Inversion. So I'm not going to go over the full details of this, but what I do want to say is that you can think of this as the application of the Ensemble Kalman filter to inverse problems. And just like the EnKF, you have two steps. You have a prediction step where you begin with an initial ensemble of particles, and then you define the sample mean and sample covariances. And then, like the analysis or the analysis step as well, what you do is you have this Kalman-like update formula which uses the sample covariances from the prediction step, and then you come up with an estimate, which is your solution right here as well. Okay. And what's very important about this presentation, which Andrew discussed as well, is that you can have different interpretations of Ensemble Kalman Inversion. These were listed on the very first slide that he had, and the interpretation that I'm going to take for this work is the work from Reynolds in 2008, and a little bit extended into the work of Iglesias from 2013, which is, you can think of this as a derivative-free optimization method used to solve PDE-constrained Bayesian inverse problems. So it is derivative-free, and the motivation is we're interested in PDE-constrained inverse problems right here. Now, the ideas come back from the 2013 paper of Marco Iglesias, and because this is a relatively new idea, or a relatively new way of thinking of Ensemble Kalman Inversion, it's not really the end goal or the end road, in the sense that you can really improve on this method with a number of different add-ons and a lot of techniques from uncertainty quantification or optimization. So when this idea came about in the 2013 paper, there were a number of limitations from the basic formulation that I show you right here. And some of the limitations which you can think of are highlighted on the board right here. Computationally, this method is quite appealing because it is derivative free, and in terms of computational cost, it really does reduce it. But in terms of the analysis, there is still a lack of analysis in terms of deriving certain results. As well as a lack of analysis, there are certain issues in terms of rank deficiency, which cause problems in stability. And what I'll show you in the numerics is that stability is quite common, because if you have the overfitting of data, this can actually cause a divergence in the relative error that you see within the experiments as well. And the last limitation that I want to tell you about is one which was originally described in the Reynolds paper of 2008, but also is inherited in the 2013 paper, which is known as the subspace property. And all the subspace property states is that if you have an initial ensemble of particles, then the solution at the very end is essentially the linear span of the initial ensemble. And just to put this in words, what this means is that if you have a particular representation of your unknown, of your initial ensemble, then the solution which you get at the very end, will also have a very similar representation as well. So this is both an advantage and a disadvantage. It's an advantage because if you have a very good initial prior belief of what your unknown is, then you can get a good reconstruction. But on the other hand, if you have very bad initial belief of what you think the unknown is, this can cause a lot of problems depending on the model itself, but also what the actual unknown you're interested in reconstructing is. But I'm going to consider this as a disadvantage as well. And since that 2013 paper, there have been a number of ways of trying to alleviate these issues on the very top. Some of these ideas include improving it through iterative regularization, which if any of you are familiar with, actually includes the regularization through this closed form you see at the very bottom of this update equation, and has a stopping criteria to see whether your results get bad, then eventually it stops it. Other ideas which have been mentioned already include hierarchical approaches, which incorporate further prior information into your unknowns to improve the inversion, and also connections with sequential Monte Carlo, and also analyzing this method in the linear case as well. So these are just some methodologies that are used in order to alleviate the top issues. But what we have been interested in is really focused on the first bullet point at the very end, which is the iterative regularization. Now, this is one form of regularization you can use. The other form is a more systematic form where you can include the regularization within your least squares functional right here. And given how, in some ways, this can be thought of as a more simplistic way, we thought it would be very nice, as well as the reasons I gave at the beginning, for the motivation to incorporate this in terms of Ensemble Kalman Inversion. So if we did this, as I said, you would include this in the form of the misfit functional. So just before I describe that, I just want to say that this update formula at the very bottom can also be interpreted as the minimizer of this least squares functional, because this is an optimizer. So if you take the usual least squares functional, which is just given on the left-hand side or the right-hand side, that's what the least squares functional is. But if you wanted to include some form of regularization, what this would include is just a penalty term at the very end, which really includes some initial belief of what your prior information is right here. And for Tikhonov regularization, if you wanted to include this, this would be the very last formula right here, which is exactly the form of Tikhonov regularization, where E is just some embedded subspace of the actual parameter space right here as well. So this is Tikhonov regularization, but there's many other forms of regularization which you can use at the very end as well. Again, to specify for this presentation, we're just going to continue with Tikhonov regularization. So now that I've mentioned Tikhonov regularization, the obvious question is, how can we incorporate this into Ensemble Kalman Inversion? Well, it's quite easy. If we start with the very first inverse problem that I showed you on the first slide, which is given on the top equation right here, then all we have to do is label U as another equation given by e to 2, where e to 2 is distributed according to a Gaussian distribution right here with a particular covariance function or covariance operator right here. And all you have to do is that you use these two equations, and if you couple these two together, then you get another inverse solver, an inverse problem which incorporates this regularization, which is at the very bottom right here. So all we've done is just label a new equation which includes the form that U actually takes, and then by coupling these two things together, we can actually get a new inverse problem at the very bottom, which is now the inverse problem that we're interested in. Okay, so very easy coupling, we can come up with the bottom equation right here. But the very interesting thing that I want to mention about Tikhonov regularization in this particular application is that there was a connection made a number of years ago between deterministic inverse problems inverse problems. And the way that you can connect these two entities or approaches is through the MAP estimate, or in other words, just this top equation right here, which is the solution of this. And what was shown is that if you include a Tikhonov regularization, which is the second equation, into this, then through the connection between these two, the actual space which you see as E is just a Cameron-Martin space, or you can think of this as being a reproducing Kernel-Hilbert space right here. And for those who are aware of it, you can just think of this as being the space of shifted Gaussian measures right here. Now this is very interesting because if you incorporate this into our inverse solver right here, what this essentially states is that you can work with a richer class of Gaussian measures from your prior distribution as well right here. So some of the techniques I said which you could alleviate the issues, this in some way heuristically can also do this because you've got smoother draws from your prior because you're actually working with the Cameron-Martin space right here. Now how we incorporate the Cameron-Martin space into the prior information I'm going to discuss in the numerics later on. But before I discuss the numerics, I think it's also always good to get some sort of insight from these sort of methods. And as Andrew pointed out, a good way to do this is to derive the continuous time limit before looking at the linear setting as well. So just as done in Andrew's case, which was for the linear case for the unregularized version, I'm going to take the exact same approach for this, where we are going to incorporate the regularization term for the continuous time limit. Now there's a number of details which I've actually missed from this presentation because of time constraints and because it would fill the board, but I just want to say that if you have the top formulation, the top equation right there, then you can get to the bottom equation right here, to the middle equation. I haven't told you what dj of k is, but of course I can tell you this at the very end. And then once you have the continuous time limit, which is just given on this slide right here, then if you take this in the linear case, and you take this in the noise-free case, then what you get is a preconditioned gradient flow structure, which is just given by the penultimate equation right here, where C of u is some preconditioned covariance, empirical covariance, and this calligraphic I is just the very bottom equation, which includes the penalty term, which I've denoted by L, the misfit functional, which I've denoted by L, but also the inclusion of the regularization term. So this is almost identical to the gradient flow structure that you get in the unregularized linear case, but when you do it for the analysis of the regularization, for the regularized version, we get pretty much the exact same ideas where you can just derive a gradient flow structure as well. So it's very nice that you can adapt these ideas to the linear gradient flow structure which was derived before. Now there were a number of ideas and analytical results that were derived from this work. I'm only going to mention two because I think these two are some of the two important ones. And the first theorem that we have is essentially stating that if you have this particular gradient flow structure right here, then what we can say is that we have uniqueness and existence of solutions right here. And the proof of this is quite simple. All you need to do is establish Lipschitz continuity, and then from this you get actually well-posedness of the bound in terms of the Tikhonov version, the regularized version. Now, as well as this theorem, the other proposition that I just want to state very briefly is that we can get a bound on the empirical covariance given by this main equation in the proposition. And to interpret this, without going into too much detail, is that we can state that the Tikhonov regularized version of Ensemble Kalman Inversion also has a collapse of the ensemble where we have this particular rate right here as well. Okay. But I'm just going to state these two ideas in terms of the analysis. The real understanding I want to get you to think about is really the numerics. So as I mentioned before, we're dealing with a Cameron-Martin space, which is where the prior information is going to come from. And as Adol talked in his presentation, one way of simulating Gaussian random fields is through a series representation. And we're going to do the exact same thing right here, where we have a Carhan-Louvy expansion, which is given as the second equation right here. And this is just a series representation if you want to simulate a Gaussian random field with, let's say, a covariance structure given at the very top. So this is your covariance operator, and then using the eigenvalues, or let's just say the eigenbasis of this covariance operator, you can actually express the KL expansion, which includes the lambdas, includes the size, but also includes some additive noise as well. So this is the usual way you would simulate a Gaussian random field if you wanted to use the KL expansion. Now, if we wanted to use the Cameron-Martin space instead of a usual Gaussian measure, rather than going through the actual details, all I'm going to state is that through some of the analysis, what you can show is that the KL expansion differs for the Cameron-Martin space, and how it differs is that the exponent of the lambda k's is a little bit different, where a is usually bigger than a half as well. So the regularity or the smoothness of the KL expansion, when you actually write it in a different form, is represented through the square root of the lambda k's. Now, because a is a little bit different to the half, and because it's bigger, what this means is that we can actually get smoother draws because the regularity is of a higher value as well. So The second equation is the usual KL expansion for what I'm going to show for the unregularized version. And if we look at the regularized version, this is just going to be the KL expansion for the third equation on the board right here. And just to give you an example of how this would look, the very top row that we have right here are just random Gaussian draws from the KL expansion that I showed you. And if we included the Cameron-Martin space, or the draws from the Cameron-Martin space of the KL expansion, all this is stating is that whatever you have on the top row, we can get smoother draws on the very bottom right here as well. And just to show the consistency of this, what I've done in the KL expansion is that I've kept the noise level the same, but the only difference that you see is, of course, with the actual parameter A, because the eigenbasis is the same. Also, the psi k is the same. So as you can see, this looks almost identical to the bottom picture, except the only difference is that you see much smoother draws. So this can be advantageous, as we're going to see in the numerics in the next few slides. So just to highlight the numerics and using the Cameron-Martin space within this, I'm going to consider one inverse PDE, which is the inverse Tikhonov equation. Now, the Tikhonov equation is a very common partial differential equation that arises in a number of applications, which is concerned with wave propagation. And just to put it quite simply, the inverse problem of this Tikhonov equation is that we are interested in reconstructing S, which is the inverse velocity function, or for people in the field using the Tikhonov equation, the slowness function. What they're interested in is reconstructing the slowness function from the shortest travel time, which is given by t, where t is the forward solution of this problem right here. And of course, we have point-wise measurements, which we take as the actual data points of this. And what we're interested in is reconstructing a particular slowness function, which is just given at the very bottom figure right here as well. Okay, so it's somewhat smooth compared to, let's say, the top figure, which we have right here. And so we're going to show a number of experiments through Ensemble Kalman Inversion and Tikhonov Ensemble Kalman Inversion, showing the benefits of regularizing this problem. So in the top figure, what we have is an Ensemble Kalman Inversion reconstruction of that particular truth right here, where the top left corresponds to the very first iteration, and then as you progress horizontally to the very right, and then eventually down horizontally again to the very final iteration, you see that it really starts quite badly, but also as it progresses through the iteration, it doesn't really learn anything whatsoever. In fact, it doesn't even really get the right structure of this right, but also in terms of the smoothness, because it's different, it really struggles to learn any sort of information from the prior itself. But if you take the Tikhonov Ensemble Kalman Inversion instead, we see that if we just take the smoothened version, we've got the exact same eigenbasis and the same noise, as you can see from the first iteration in the top picture to the first iteration in the bottom picture. This is just the smoothness, which is different. If you include this smoothness into the Tikhonov version, then you can see a much big improvement in terms of actually reconstructing this image, which looks a lot similar compared to the very last iteration of the Tikhonov version compared to the last version of the Ensemble version. And the last experiment that I want to show you, or the last bit of this experiment that I want to show you, is the case where if we can actually consider this KL expansion, but we remove any notion of the noise itself. So if we remove noise from this KL expansion, all we have as an initial ensemble is just essentially the eigenvectors of this covariance operator. And as you can see right here, we have got a particular eigenvector right here, both in terms of the initial ensemble for EKI, but also TEKI. And the advantage of using this KL basis is that we actually get a smoothened version already from the very top figure. But if we incorporate the ideas of regularization to the KL basis, which is already smooth, we start to see a little bit of an improvement already between the regularized case with KL, but compared to the unregularized case as well. And to highlight the differences between these plots, I've just showed the relative error and the data misfit. And the most staggering thing that I want to show you from this is that if you look at the unregularized case, which is the red plot right here, as the iterations start to progress, you really start to see a big decline in the relative error. And then as you actually go below the noise level, which is given on the right-hand side figure because of the overfitting of data, it starts to see a divergence in the relative error. And this was the actual real motivation of understanding this method. How could we actually improve upon this divergence just by incorporating regularization methods? And as you see, if you include any form of regularization, or even if you include a KL basis, we start to get an improvement as well. But the overall, let's say, in a naive way, the optimal method of doing these sort of PDE-constrained Bayesian inverse problems is to use the Tikhonov Ensemble Kalman Inversion with regular draws as well. So to conclude, the real motivation, as I've mentioned behind this presentation, is to see how can regularization be incorporated into Ensemble Kalman Inversion and what sort of benefits we can get from this. I showed that it's very easy systematically to actually incorporate this form of regularization to EKI. And I showed a number of results which are very important, such as well-posedness, and showed you that if you could do this numerically, then you can get improvements which can move away from the divergence of the error because it incorporates prior information as well. So I think the interesting thing about this presentation, but also Ensemble Kalman Inversion, is that you can really work on a number of other interesting things which take motivation from the Bayesian UQ side, but also the optimization side. So my take-home message really from this presentation is that when you're dealing with PDE-constrained inverse problems, let's say of this inverse solver and other ones, that the combination of UQ techniques and optimization techniques can be quite powerful, and we've done this through a number of different works as well. And I just want to conclude by showing some key references that we have that we've used for this work, and hopefully this work will be finished within the next few weeks. So, thanks.
Thank you very much.